Hi, my name is Ondřej Uhlík and I would like to present my research where I focus on real-time RSET estimation based on simulation datasets and machine learning techniques. First question of my research is why do we really need real-time estimates of evacuation process? I believe the answer is quite simple and it is yes. One of the challenges in our current global safety situation is the ability to respond promptly in a case of an emergency. We are accustomed to using evacuation models in a certain way to test the different scenarios and prepare our buildings or areas for future specific emergencies. The idea of this work is not to use agent-based evacuation model in the classic way for civil engineering adjustments or to create evacuation plans, but rather to respond effectively based on real-time local data from camera systems and simulation outputs. For this kind of task, we cannot use agent-based evacuation models in the classic manner, as we don't have time to properly calibrate them with local occupancy data during an emergency and then run simulations due to computational demands. The idea is illustrated in the diagram on the screen. Green parts of the diagram are subject of this work and the blue parts serve for the bigger context of the presented idea. We can use modern computer vision techniques to gather long-term calibration data and improve the accuracy of the evacuation models. And the ability to gather this data in real time allows us to feed it into a machine learning model, which can provide estimates for simulation outputs. We refer to this machine learning model as an evacuation meta-model, as it serves as a model of an evacuation model. These estimates can be utilized by security management, facility management, or security forces to make data-based decisions. The aim of this research is to introduce and test a method for constructing a meta-model using a case study to estimate RSET as a key indicator of evacuation process. In this study, we compare 9 evacuation meta-models to see which fits best for this type of task. For this purpose, we created an evacuation model of a building using Pathfinder software, then generated a simulation dataset with 100 samples based on 3 variables using a method for generating quasi-random numbers called Sobol sequence. This method allows for uniform coverage of the interval for each variable. After that, we perform classic Monte Carlo simulations with 20 runs, so in the end we performed 2000 simulations. Afterwards, we used this simulation dataset for analysis and to generate new machine learning dataset, which was used for training meta-models using a nested cross-validation technique. 9 standard machine learning models used for regression tasks were chosen for comparison with 3 evaluation metrics, R-squared, maximum error, and mean absolute error. So the used machine learning models are ordinary least square, polynomial model, K nearest neighbor model, random forest, gradient boost, extreme gradient boost, support vector regression, Gaussian process, and artificial neural network. Nested cross-validation was used for perform machine learning whole process, and the nested cross-validation means that we use classic k-fold cross-validation twice. For the first time we use it for searching for the best hyperparameters of each model architecture, and then we use outer validation to train the optimized meta model and train it on the whole data set, not just one part, so that we know that the meta model performs well or worse on the whole data set. As the object of for the case study, we used a floor of a university building. The building has a capacity of 300 occupants, including personnel and students. The evacuation path goes through the main hallway, past safety grills, and onto the stairway, which you can see on a video. One exit of the model is set on a 3rd floor, right after occupants reach it. The floor is divided into 2 sectors, A and B, allowing us to consider different occupancy scenarios. In other cases, the sector could separate the floors, for example, or bigger parts of a building. Pre-evacuation time was calibrated with logarithmic normal distribution. And the RSET variability of performed Monte Carlo simulations ranges between 100 to 280 seconds. So the main task for the machine learning meta model would be to cover this variability and learn patterns in simulations to be able to know causes of this variability of RSET. A simulation dataset is composed of 3 variables, as I mentioned: the number of occupants in a sector A, number of occupants in a sector B, and the mean walking speed of occupants. This dataset is not used for metamodel training, but for creating a dataset of simulations. The machine learning dataset is then created with 7 quantitative spatial input features: the number of occupants, minimum, mean, and maximum distance of occupants to the exit, minimum and mean distance between occupants, and mean walking speed. The goal was to be able to enable the meta model to determine how many people are in a building, where they are located, and what their walking speed distribution is in a very general way, so that it is easy to reproduce this data set, to create generation of this data set for engineers. Dependent variable is RSET mean, which is the average for 20 Monte Carlo simulations. It should be mentioned that pre-evacuation time cannot be an input for a machine learning model in this manner, since it was calibrated with one distribution across the entire population in agent-based evacuation model. So yeah, we expect this pre-evacuation time distribution is valid, so it doesn't make sense to include it as an input for the meta model, and it behaves as a bias for the meta model, because the meta model doesn't know why people respond later. Why is RSET bigger in some simulations? So the purpose of this study was also to see how meta model can deal with this bias. Features were chosen to be as general as possible, so they can be used in other buildings and scenarios, as I mentioned. Additionally, each of them can be computed in real time through computer vision algorithms. We can move to results right now. Here is a table summarizing the results of R-squared, maximum error, and mean absolute error. The result shows that the ANN meta model achieved the best results across all evaluation metrics in terms of the ANN meta model's ability to generalize on this type of training data and set of input attributes. The prediction results appear to be sufficiently accurate in the context of the evacuation model. However, almost every meta model shows some degree of overfitting. So we can see that performance on train data is much better than on test data. This could suggest that the dataset of 100 samples is too small, and the meta model needs more data to better learn from the given data population. Despite this overfitting, the meta models generally produce decent results, with ANN performing within the mean absolute error metric 3.81 per seconds. So perhaps this is more evident in the residual plot created of the ANN meta model, which shows residuals for all 20 repetitions of nested cross-validation, because nested cross-validation was also repeated 20 times, so we can make statistics over ANN or some other meta model's results. As you can see, the plot indicates that the vast majority of residuals are distributed in the range of -5 to 5 seconds. So this fact once again confirms that the errors produced by the meta model are on the order of a few seconds. Given that the evacuation process involves many phenomena, as we all know, that are generally difficult to model, such as behavioral or decision-making processes, and these phenomena can lead to higher deviations. This kind of deviations that we present, the deviations from simulation outputs, seems marginal in this context. given it is a few seconds. This plot shows the contribution of each machine learning dataset feature to the metamodel's estimations. Features are ordered from top to bottom according to their impact. Higher means greater impact. So we can observe that the mean walking speed feature has the highest impact and contributes to RSET mean with a maximum of approximately 30 seconds. The second feature is the number of occupants, which is also intuitive that this feature has great impact on, or high impact on RSET. Then there is the mean distance between occupants. A lower distance, which means high density, leads to higher RSET mean, which makes sense since higher density leads to lower walking speeds. As the mean distance to the exit increases, RSET mean also increases, so basically it means if people or occupants are more far away from exit, it means that they have higher RSET, so it makes sense. The last three features contribute the least to the estimation. So we reached the end of the presentation. This work demonstrated that machine learning models can be a useful tool for real-time estimation based on simulation dataset. However, we must be very careful when deploying them in real-world tasks, as this caution applies to any evacuation model in general, of course. This work is a proof of concept pilot project and should be further expanded with follow-up research, particularly in the area of optimizing the simulation dataset in terms of its scope, and the machine learning dataset in terms of selection of input variables. Thank you for your attention.